Have you ever stopped to think about how that works? How a whisper, just a little vibration in the air, can travel across a room and turn into a clear thought or even a feeling inside your head? Well, today, we're going to dive deep into that. We're taking a journey inside one of the most amazing pieces of tech you'll ever own, your ear.
And it all starts right here, with this page of notes. I know, it looks a little chaotic, maybe a bit complex, but trust me, everything we need is in this diagram. It's basically a roadmap for how we hear the world and how we manage to stay upright in it. So let's unpack it, piece by piece, and turn this sketch into a story that makes perfect sense.
So, this is the big question, right? This is the mystery we're cracking today. It's this incredible process that mixes physics, mechanics, and biology, and it all happens faster than you can even blink. So, let's follow a single sound wave and see where its remarkable journey takes it.
To really get started, let's learn the ear's official name, the statoacoustic organ. Now, what's so cool about this name is that it perfectly spills the beans on its two-for-one deal. Acoustic, that's for hearing, obviously. But stato, that refers to staying still, to balance. It's a dead giveaway that this organ is a master multitasker.
So, on one side of the job description, the ear is processing mechanical sound waves from the air, which gives us hearing. And on the other, it's processing the mechanical movements of our own bodies, which gives us our sense of balance, our equilibrium. It's an incredible design. Let's tackle the hearing part first.
The journey for every single sound you have ever heard, well, it starts right here, with the part of the ear you can actually see. We're talking about the outer ear, which is basically just a big, beautifully designed funnel.
The process here is actually pretty simple. First, the pinna, the cartilage part on the side of your head, it collects all those sound waves. Then they get funneled down the ear canal, just a simple tube, until they run into a roadblock, a taut little drumhead called the tympanic membrane.
But get this, the outer ear isn't just a passive funnel. As our source notes point out, it's also doing some preliminary filtering. You can think of it like a natural sound engineer, giving certain frequencies a little boost. This actually helps your brain figure out where a sound is coming from before it even gets deep inside. Pretty smart, right?
So once that sound wave smacks into the eardrum, it passes into the middle ear. And this is where things get really mechanical and a whole lot louder. Welcome to the amplification room.
How much louder, you ask? Well, the tiny little bones in your middle ear, they're called ossicles. They work together as a lever system that can crank up the power of that vibration by up to 20 times. 20! That's a massive power boost, and it's absolutely crucial for what happens next. This tiny space turns a whisper into a shout.
And the gatekeeper to this whole amplification process is that tympanic membrane, what we all call the eardrum. It is the critical link in the chain. It's what catches the energy from the airy outside world and physically hands it off to the solid mechanical world of the middle ear.
Okay, so now we've got a really strong mechanical vibration. But so what? Your brain doesn't speak vibration. It speaks in electrical signals. So the real question is, how does the ear perform that final bit of magic and translate the message? For that, we've got to go even deeper.
And that brings us to the inner ear. If the outer ear is a funnel and the middle ear is an amplifier, then the inner ear is the conversion chamber. This is where raw mechanics get turned into sophisticated biochemistry.
So that big amplified vibration from the middle ear, it slams into the fluid-filled inner ear and sets off this incredible chain reaction, a total cascade. First, one fluid vibrates. That makes a tiny membrane vibrate, which makes another fluid vibrate, and that finally vibrates one last crucial membrane. It's like a microscopic set of dominoes falling over.
And this is the moment. This is the whole point. When that final membrane moves, it physically forces specialized little cells to open up, which creates an electrical response. This releases chemicals, neurotransmitters, and just like that, the mechanical energy from a sound wave has officially become a signal our nervous system can actually read.
The signal has been created. The message is finally written in a language the brain can understand. Now it just needs to be delivered. This is it, the final leg of the journey, from the ear to the brain.
So this brand new electrical signal, which is carrying all the rich information about the sound's pitch and its volume, it zips out of the inner ear and jumps onto a dedicated superhighway called the cochlear nerve.
And its final destination? The cerebrum, the main part of your brain that handles conscious thought. And it's only here,
only after that signal gets processed and interpreted by your brain that the little vibration that started in the air is finally perceived by you as sound. The journey is complete.
But, that's only half the story of this incredible organ. Remember that name? The statoacoustic organ. We've just covered the acoustic part. We cannot forget about its equally important, and maybe even more amazing, second job.
So let's talk about that secret second job. Let's talk about the power of balance. The thing that lets you stand and walk and move through the world without constantly falling over. And the real difference between these two systems boils down to the response. Both hearing and balance start with a mechanical stimulus, a vibration for hearing, the movement of your head for balance. But here's the key. Hearing creates an electrical response that leads to a perception. Balance, on the other hand, creates a dynamic response that leads to immediate muscle adjustments to keep you stable.
So how does it work? Well, a totally different part of your inner ear, the semicircular apparatus, is busy detecting your head's movement. As you move, fluid inside these canals sloshes around and sends a signal down the vestibular nerve. And that signal goes to two places at once. To the cerebellum for all the super-fast automatic adjustments you don't think about, and to the cerebrum for the conscious ones. This is why, by the way, an inner ear infection can make you so dizzy. It's messing with that fluid system and sending faulty balance signals to your brain. This table from our notes is the perfect cheat sheet. For hearing, you've got the cochlea talking to the cerebrum via the cochlear nerve. Simple. For equilibrium, you've got the semicircular apparatus talking to both the cerebellum and the cerebrum via the vestibular nerve. Two totally separate but parallel systems. But here's the final, mind-blowing detail. These two separate nerves, one for what you hear and one for how you're moving, they actually merge on their way to the brain. They braid themselves together to form one single information highway, the auditory nerve, sending both streams of data, sound and balance, to your brain at the exact same time.
Which leaves us with one last thing to chew on. If the signals for hearing and balance start in the same place and travel together down the same nerve, why do they feel so profoundly different? Why can one signal create the incredible feeling of joy for music, while the other creates the primal gut-wrenching terror of falling? Now that's a question about the real magic, how the brain turns simple data into the rich, complex thing we call human experience.